Laboratory, we're going to focus on what we call two-port devices. Now, two-port devices, there's many of them. The most typical examples are attenuators, sometimes called a pad. Okay, this is a calibrated loss element. That's very useful for us because gain is very difficult to acquire at RF frequencies. So having a calibrated loss can almost allow you to operate with a calibrated gain. Because if we have an amplifier and apply a calibrated loss to it, then we can adjust the power level. So I'll give you data on this. Here's typical filters. Of course, filters are classic two-port element. There's an input and an output. They come in all different varieties. Here's a bandpass filter. I believe this one is a low-pass filter, as is this. Low pass and band pass are two of the most common filters we use in RF, and occasionally we'll use high pass and rarely band reject, which is a notch filter. Here's a couple other filters. These are all over here is SMA connectors, the small ones. Sometimes it's gold, but the small SMA type connector. Here we have some type N filters. This is a 700 megahertz low pass filter, 1200 megahertz low pass filter, and a 4100 megacycle or 4.1 gigahertz filter. Notice the links, lower frequency and then higher frequency. Here's two filters. I'll open one of these up for you. There's a low pass filter, and here's a high pass filter. By the way, if you look at a characteristic curve on a filter, generally instead of plotting like a traditional Bode plot and gain, they plot loss. So this being a low pass filter, it has very low loss and then high attenuation. So filters and filter designers usually talk about attenuation rather than gain. Here's a selection of amplifiers. We have smaller power amplifiers. I'll test one of these for you. These come from a company called Mini Circuits, and I'll send you some data on there. Higher power usually means that you obviously you have some heat dissipation. So these two amplifiers have heat sinks on them. Of course, amplifiers must have power, right? So there's a plus minus 15 volts to run that. And this one likewise has a plus 15 volt supply requirement. So we'll do a little test on that. Now, these three attenuators, filters, and amplifiers aren't the only two-port devices. We sometimes use devices like this, which is an isolator. Okay, very unique device used in RF. If I want a signal to go one way, right, then I can use an isolator, which is a specialized, inside it's actually got an extra termination port, which allows the signal to go this way, but no reflection to come back. It's actually very similar to the directional coupler we talked about in waveguide. Signal, in this case, can come from one end, but the return signal goes a different path. In the isolator, it's terminated. Other devices that can have multiple ports, of course in 335 we talked about mixers, so L, R, and I for local oscillator, RF signal, and intermediate frequency. That's a classic 3-port device. Here is a 2-port divider, or no, this is a combiner, I'm sorry. We have input 1, input 2, and then output. There's a termination port over here, so you put a load here, and that combines two signals into one. Here's the opposite. Here's a divider. This happens to be a 3-way power divider, 800 to 3 gigahertz, 800 megahertz, 3 gigahertz. We have an input signal, and we want to split it into 3. The trick on this kind of design is we want to evenly split these signals, not only in magnitude, but also in phase shift. Here's a very unique device. I picked this up at a swap meet years ago. This was a what we call a duplexer. And a duplexer is a 3-port device. We see 1 port here and 2 ports here. And a duplexer allows us to combine an antenna to a transmitter and a receiver. This one happened to come out of cell phone version 1. They called the AMPS or AMPS system. And this operates, I'll show you the data, just under a gigahertz. So I would connect my antenna here, and then a transmit signal. I'll show that over here. The transmit signal's here, and the receive signal is here. I probably won't give you data on this, but it's 2 filters operating at different frequencies connected to a common device. So multi-port devices are also common, but we're going to focus on the 2-port devices, attenuators or loss elements, filters, different filters and frequencies, and then finally amplifiers. And I'll try and give you some data on the isolator, just so you'll get a sense of different characteristic curves. So the calibration process is very similar on a 2-port as a single-port device, like an antenna, except now we have to calibrate both ports. So you push the cal button and calibrate menu, and in this time, instead of doing an S11 port or an S221 port, we're going to do a full 2-port calibration. So we press 2-port calibration, and we see that we have 3 options or selections. First, we have reflection test. Now the reflection test, you'll notice, uses forward open short load and reverse open short load. So we are going to calibrate this port with an open short and load, and this port with an open short and load. So we're going to calibrate both the input and output, or the forward and the reverse port. These are the transmission forward, reflection forward, reverse, reverse. Now after we are done with that, we'll go back to what are called the transmission coefficients. So transmission means I'm going to do between this port and this port. And there's actually 4 measurements, from forward to reverse, from forward to a match, from reverse through connection, so a signal going this way, and a reverse match. Now fortunately, we can do this with 1 connection. So we can do all of those, and that's why this selection, do both forward and reverse, is available. Lastly, we have what's called an isolation calibration. Now isolation is measuring how much this port is not connected to this port. Now that can be important in certain devices, but fortunately for us and our devices, we can omit the isolation. So most of our calibration then is going to be through the reflection. So I'll set up for that. So I've started the initial calibration. On the forward port, I have a termination of 50 ohms. And on this port, I have an open. You can see that arrow pointing to an open. So I just go up to my supply on the forward or the network analyzer, and I press load. You hear the beep saying it took the measurements. And on the reverse, I'm going to do an open. And then you obviously do the other connections. So I can flip this around. This is an open on one end and a short on the other end. And then you go through. I'll skip that part to keep the video shorter. So I have completed on the forward port the open, the short, and the load, just like a single port. On the reverse port, I've done my open, I've done my load, and lastly, I'm going to do my short. So you can see the short label there, and so I'll press that button. It does the measurement, and as before, you must press standards done. Now the reflection test is done as it's got the underline. Next will be transmission. So when we do a transmission test, we're going to put a cable in between the 2 ports. Now this cable length represents a little bit of phase shift. So at higher frequencies, you must be a little bit more deliberate and careful in the calibration, but we're going to be working at lower frequencies, and so this cable will do fine. So I've connected my cable between the forward port and the reverse port, and then I'm going to come up to my screen and do both forward and reverse. You'll hear it beep 4 times as it goes through, forward match, reverse through, and reverse match. The match itself is actually inside of the network analyzer. So we'll press the button. The screen changed 4 times. Now we are done with the transmission, so we have an underline there. And under isolation, we're simply going to omit isolation. In the devices we're testing, we don't need to worry about that, so we'll omit it. But we must complete that step. And then we are done. All right, now we are ready to insert our device and take some measurements. So before we test this pad, or 3 dB pad we call it, or attenuator, let's look a little bit at the circuit. Okay, there's 2 types of pads, typical. This is called a T pad for this T shape. It involves 3 resistors. So 3 resistors. The input and output resistors are the same value. They must be, because the impedance looking into this device with this port terminated will be 50 ohms. And so it must look the same both directions. R2 is the other resistor, and between those 3 you can calculate the conditions, 50 ohm input and output, and a loss that we want. Now the loss is of course 20 log V out over Vn, or 10 log P out over Pn. The loss typical would be 3 dB, that's equivalent to a 0.707 voltage ratio, 6 dB equivalent to a 0.5 ratio, 10 dB is another common value, 14 dB would be another value that we have in the lab. So we have 3 dB, 6 dB, 10 dB, and 14 dB. I'll do at least one of those to show you how it behaves. Now there's another option on a pad. We have what's called a pi pad, so called because of this pi shape in the middle, pi right there. And in this case, the middle resistor is the different resistor. These 2 resistors are the same. The impedance of the input when we're terminated in 50 ohms will be 50 ohms. So if I have a 50 ohm load on the output, then this will look like 50 ohms. And that's important for matching. And that's true on both the pi and the T pads. So these pads that I'm going to test are actually T pads. If I open this up, you'd find a resistor R1 connected to the center conductor, and this is the outer conductor. They're kind of funny looking resistors because the middle resistor is actually kind of a disc, because it goes from the center conductor to the outer conductor. And then the 2 resistors on the input and output are just in the series path from the center conductor. I probably won't show you that, but I've opened them up before for that. Okay, I'm going to switch over to the display screen for you. I think it'll be easier for you to watch instead of me trying to handheld the camera. So, but what I've gone and done my calibration, and then we're going to look at the measurements. So we have 4 measurements in 2 ports. We have forward measurement, which is the S11 connection. We have transmission, which is from port 1 to port 2. So that's called the forward measurement. We have the reverse measurement, which is from port 2 back to 1. So, and then the reflection port on, or the output measurement. So we have input, forward transmission, reverse, and then output. Input, output, forward, reverse. Always on the network analyzer. Now, knowing what a pad looks like, first let's look at the transmission characteristic. So I've selected transmission, and you'll see that there's a little bit of loss. The red line is our reference. Okay, let me change the scale and we'll be able to read that value a little closer. So I have repositioned my reference, which is the red line, just to this position. It's just like your scope, adjusting up or down. And this is my signal measurement, yellow. I changed my dBs per division to be 3 dBs because this is a 3 dB pad, right? And you can see I'm taking measurements at 500 megahertz, 1 gigahertz, 1.5, 2 gigahertz, and finally 3 gigahertz. And you can see the values that are listed on the measurements, right? Here's measurement 1 at 500 megahertz. The loss is minus 3.03 dB. Marker 2 is at 1 gigahertz, and it is equal to minus 3.07. So that loss is very consistent among the frequencies. This is why pads are very useful for us. 1.5 gigahertz minus 3.1. So a little extra loss there. 4 minus 3.1, that's 2 gigahertz. And finally, the last marker is at 3 gigahertz and minus 3.2. But from all frequencies up to 3 gigahertz, we have very little variation in the loss. This is what makes pads so nicely. Now I'm going to change to another measurement. So we looked at the forward measurement, but remember the pad is a input-output device. So I'm now going to look at the reverse measurement. Now, hopefully, right, I changed to reverse, but what happened? The screen stays the same basically. Because remember how the pad is made. We have R1, we have R2, and then R1 again on the pad, the T-pad, right? So as long as R1 and R1 are very similar or very closely matched, the input to output and output to input will be identical. Now we need to look at the S11 and S22. Now we need to think about this, right? Now S11 is the forward reflection coefficient. So if this is a 50 ohm device, the forward reflection should be 0. If the forward reflection is 0, that means the return loss, which is the reflected over the incident, should be a very large negative value. And that's what we see. It's so far negative, it's below the screen. So this is 3, 6, 9, 12, 15, 18, 21 dB. In fact, if I look at the values, they're actually being read. Let me change the scale here to be 10 dB per division. That'll be a little more reasonable. So that's 10, 20, more than 20 dB. Remember, 20 dB is a 1 out of 100 power level, so it's a 1 out of 10 voltage level, right? And here we see, even at 3 gigahertz, it's minus 20, 4 gigahertz, it's minus 23. If we go down to 500 megahertz, marker 1, it's minus 36 dB, which means greater than 1 part out of about 4,000 in power, right? So very good match. So a low signal here means a good match. Now let's look at S22. If you think about S22, what would you expect? Well, S22 is looking at the output match. S11 was looking at the input match. So we would expect something very similar on S22. Now it's different because internally those resistors are a little different, and the R1 on the output and the R1 on the input are a little different. But still, we have pretty good loss across that band, more than 20 dB. More than 20 dB is a pretty good match. More than 30 dB would be a great match, 1 part out of 1,000. More than 40 dB would be fantastic match, 1 part out of 10,000 in terms of power. But this tells us that the match is very good. Now, in this level and S parameters, we're going to talk mostly about dBs, not about reflection coefficient, but we know we can change between reflection coefficient, VSWR, and return loss through equations. So that is the pad, the 3 dB pad. So I have changed the element of test to a filter. Okay, so now on a filter, we know what filters should look like, right? There should be this happens to be a low pass filter. We should expect to see a kind of passing frequency and then a loss, right? So I'm going to select my forward path, right? And we see this happens to be a 1200 megahertz or 1.2 gigahertz filter. And we see at low frequencies, everything gets through. The red line is 0 dB, and you can see the loss at 500 megahertz is equal to 0.1 dB. Not much loss at all. 2, which is 1 dB or 1 gigahertz, it's minus 0.26 dB. I'm going to move to 1200 megahertz on marker 3 so we can see what that is. So I'm at 1.2 gigahertz, which is the design frequency for this filter, and it should be close to 3 dB. It's a little off there, minus 1.8 dB. But normally filters are designed for that 3 dB frequency. If I adjust the frequency a little bit, I can find exactly where it is. So it turns out at 1.209 megahertz is the 3 dB frequency loss. Now that is S21. That means output over input. Output to input 1. Now what about S12? Well, S12 is input over output, or the reverse characteristic. And since this is a filter, we would expect to see almost the identical response, which is what we see. Notice that this now it's a little different loss at that frequency, because inside the filter there's different elements, so viewed from each end they're going to be a little different. But S21 certainly matches. Now what about S11 and S22? Well, let's think about this, right? At frequencies below the cutoff frequency, we expect everything to pass through the filter, almost at no loss at all. If everything passes through the filter, that means on frequencies below the cutoff, we're actually looking at the other end of the network analyzer, port 2, which is a match. So we expect a match in this region, and then where the filter is rejecting or not letting through the signal, we expect reflection. So no reflection, reflection on a filter. Now, no reflection or a match means that this response will be low, and then reflection means it will be high. So here is S11, and that's exactly what we see. Here's the return loss term, almost not quite 20 dB for all frequencies, but below the critical frequency or low pass frequency, we have return losses in maybe 16 dB or something like that. And then 4 and 5, which are 2 gigahertz and 5 gigahertz, well above the cutoff frequency, we have total reflection. Total reflection means 0 dB return loss, because we're getting everything back that we sent in. And of course, S22 should look very similar, and it does. because going from the output or the input on the match should be 50 ohms. So that's the filter, the more characteristic S21. You look at the attenuation down here, 10, 20, 30, 40, 50, 60, 70 dB and more of attenuation. Very good filter. All right, I'll make those printouts. So for the last measurement, at least in this lab, we're going to connect an amplifier to the network analyzer. Now we know what an amplifier does. It provides gain from a forward path to the output, input to output. Of course, we must have power supply. In this case, this is a 15-volt amplifier. So we expect that the input will be a match, 50 ohms, and the output will also be matched. But what's going to be different is that the output is going to be greater than the input, at least we hope so, right? And so S21, which is output over input, should be greater than the reference, or 0 dB. Now, alternatively, we expect there to be no signal gain from the output to the input. That would be a feedback term, and amplifiers, we don't like to have feedback on the amplifiers. So we expect match for S11, we expect match for S22, we expect gain S21, and no signal or very little signal on S12. So let's see what we get. So I have connected my amplifier to the network analyzer. I'm going to look at S21, which is the forward gain term, output over input. Now, I haven't powered on the amplifier yet, so we're getting almost no signal, right? Red would be the 0 dB line. So network analyzers, you need to be very careful on the power settings. They're very sensitive receivers and you don't want to overload them. Most of them have power protection, but you just have to be careful. Okay, I'm ready to power on the amplifier, and you can see the signal jump up, right? So red is my 0 dB line, so I'm getting 10, 20, 30 dB of power gain. This amplifier was rated to 1 gigahertz, so let me add some markers here. 500 megahertz, marker 2, 1 gigahertz, marker 3, 1.5 gigahertz, marker 4, 2 gigahertz, and finally marker 5, 3 gigahertz. And we will go back to look at marker 3, which I know is pretty close to the max range. So this amplifier is giving us around 28 dB of gain at 1 gigahertz, or 1.5 gigahertz. 1 gigahertz is the rating. So over 30 dB of gain. And it's pretty flat. Not as flat as the attenuator, but pretty good. Okay, now we want to look at S11. Now remember, a network analyzer, we'd like to see that it looks like an input match. And again, we see return loss. It's just a little less than 10 dB at that point. So we do have some reflected energy on that input port, but that's 1/10 power. So not a bad match for that system. And that's up to 1 gigahertz, a little better, up to 500 megahertz, almost 20 dB in that region. It's still pretty well matched out to 3 gigahertz. Okay, now we're going to look at the output port. So now I've looked at the output port, and again, somewhat similar to the input port. The return loss is in the order of 10 dB in the amplifier region. It gets less than 10 dB in the above 2 gigahertz or so. So that's not unusual that you can see that happen at higher frequencies. But at the location where it's designed for 1 gigahertz, it's pretty good return loss. Okay, now we want to look at S12, which is the interesting one in an amplifier. Now, S12, right? So S12 is the input from the output. And what do we expect? Going back through the amplifier, we expect minimal signal, and that's exactly what we see. We see less than 10, 20, 30 dB of signal getting through, so that's really kind of noise, almost 40 dB. So this amplifier is behaving very unilateral, meaning it's sending data from the input to the output without much feedback signal. Again, there's our gain. There's our return feedback signal. There's our input match. And lastly, our output match. So I'll plot those for you and give you that data. That's the end of the two-port network analyzer measurement.